Today's topic is Mazur's Chapter 5, Energy. And I guess, as usual, you have your choice whether to watch the lecture or to read the book, or you might do something in between. If you want to follow the slides that I go through here, they are at phys8slides05.pdf in the positron/p8/files area. If you do read through the book, the printed book is fine, but if you are looking at the PDF, then checkpoint 5.13 has a typo. He said yes, but he means no here. He really means to write no at the very beginning. That's all. So let me start with some definitions, which is going to be a little bit of a boring set of definitions, but this allows me then no longer to assume that you've read the book. So Chapter 4 on momentum introduced our first example of a conserved quantity in physics. The momentum, P, equals mass times velocity. So the momentum vector points in the same direction as the velocity vector. It's multiplied by the mass, which is a scalar. So Chapter 5 introduces a second, one of our great conserved quantities in physics. It's called energy. Energy is a scalar, while momentum is a vector. Like momentum, energy can be transferred from one object to another, but it cannot be created or destroyed. So remember, we said that an isolated system is a system that momentum cannot get in or out of. And we will analogously say a closed system is a system that energy cannot get in or out of. So energy can be transferred from one object to another, or it can be transferred to or from the environment that surrounds a system, but it cannot be created or destroyed. And again, we say that a closed system exchanges no energy with its environment. And then because energy is a conserved quantity, the energy of a closed system is constant. Similarly, we said that because momentum is a conserved quantity, the momentum of an isolated system is constant. In physics, the SI unit of energy, the Système International unit of energy, is the joule. We write capital J for joule. Much of our everyday experience with energy relates to chemical energy, which is stored in fuel and in food. So we use energy in chemical form for heating, for transportation, and we use energy in dietary chemical form for sustenance. So if you took high school chemistry, you may remember that a calorie in chemistry is 4.18 joules. And in nutrition, a food calorie, at least in the United States, I usually write capital C for a food calorie to distinguish it from the chemistry type of calories. So one food calorie is 4,180 joules. So a chemical calorie is 4.18 joules. A food calorie is 4.18 kilojoules. And in fact, outside of the US, if you look at the nutrition information on a soda can or other food package, you'll usually see that the energy content is listed in kilocalories, which is equivalent to a US dietary calorie. Anyway, the first form of energy that we will consider in physics is kinetic energy. Kinetic energy is the energy of motion. And you might have seen before that kinetic energy is 1/2 mv squared. So that's 1/2 times the mass times the square of the speed of an object. Okay, so the expression for the kinetic energy of an object of mass m moving at speed v is 1/2 mv squared. This is assuming the object is not rotating. That will add an additional contribution for an object which is rotating about its own center of mass, but we won't worry about that until we get to Chapter 11. So when an isolated system of two objects collides, the momentum of the two object system is constant. So the total momentum remains unchanged. And this was the main topic we addressed in the previous lecture and worksheet that went with it. So the momentum law does not tell us the whole story when two objects collide. So watching two objects collide on a track, we can identify 4 distinct types of collision. And what distinguishes these 4 types of collision is whether or how kinetic energy is transformed to or from other forms in the collision. So we'll see in some cases the total kinetic energy of the two objects after the collision is the same as the total kinetic energy of the two objects before the collision. Other times we'll see it's reduced partially. Other times we'll see it's reduced by as much as it can possibly be reduced while still being consistent with momentum conservation. And then there's yet another case where something like a compressed spring releases its energy in a so-called explosive separation, so that the kinetic energy of the final state is bigger than the kinetic energy of the initial state. So in an elastic collision, the total kinetic energy is constant. In other words, if you have the kinetic energy of object 1, you have 2 objects, object 1, object 2, so you could say K1 final plus K2 final equals K1 initial plus K2 initial. Or another way to write that is you could say 1/2 M1 V1, well, let's just do x coordinates, I guess, V1 x final squared plus 1/2 M2 V2 x final squared equals 1/2 M1 V1 x initial squared plus 1/2 M2 V2 x initial squared. I'm just doing x components for now. Okay, so that's what happens in an elastic collision. And the sum of the 2 kinetic energies at the end is the same as the sum of the 2 kinetic energies at the beginning. So the total kinetic energy in the final state is the same as the total kinetic energy in the initial state. That's elastic. In an inelastic collision, and sometimes it's tricky to pronounce inelastic, so you know it's in and not an. In an inelastic collision, some of the 2 objects' total kinetic energy is transformed into other forms. So if it's inelastic, then instead of this being equals, this would be less than. So then the kinetic energy in the final state would be less than the kinetic energy in the initial state if the collision is inelastic. Okay, so some kinetic energy is somehow transformed into some other form. Often that form is heat. Sometimes that form is like the mangling of the bumpers of a car. In a totally inelastic collision, the 2 objects stick together. And it's fun to watch videos of that, and it's also fun to solve problems in that circumstance because one variable in the final state is immediately eliminated. So the math is always nice and easy when you have a totally inelastic collision. And then, okay, in an explosive separation, you have 2 objects that are initially stuck together and they separate, usually due to the release of a spring or some other form of stored energy. Now, your eye can most easily distinguish the 4 types of collision by looking at the relative speed of the 2 objects after the collision versus before the collision, or the explosive separation. The relative velocity of objects 1 and 2 is the difference in the 2 objects' velocities. So it's v1 minus v2. It's the difference of those 2 vectors. And considering only x components for now, so we're working in 1 dimension, the x component of the relative velocity of objects 1 and 2 is v1x minus v2x. And this is kind of like you look out the window when your car is going down the highway and you can look at the relative velocity, or without a magnitude, the relative speed of another car. So you say, how fast is our car going relative to you? So you subtract your 2 velocities, that's the relative velocity, and then you can take the magnitude of that difference, and that's the relative speed. So the relative speed is the magnitude of the relative velocity. So if you take the difference of the 2 vectors and you take the vector norm of that difference, That's the relative speed. We're going to work in one dimension for now. So in one dimension, it's just v1x minus v2x, the absolute value of that difference. And you will often see in the textbook the symbol v12. So it's just v with a subscript 1, 2 to mean the relative speed of objects 1 and 2. So if you see v12 with no arrow over it, that's the relative speed. In a totally inelastic collision where the two objects stick together, the relative speed of the two objects is 0 after the collision. Okay, so after the collision, the two objects' relative speed is 0. In an explosive separation, the relative speed of the two objects is 0 before the collision, but it's non-zero afterward. It turns out that for an elastic collision, for a collision which is elastic, the relative speed of the two objects is unchanged by the collision. So this turns out to be a much easier way to describe a collision which is elastic. For a collision which is elastic, it's a true statement that the total kinetic energy before equals the total kinetic energy after, but a much easier way to express that is that the relative speed afterward of the two objects is the same as the relative speed beforehand of the two objects. That turns out to make the math much easier. It's also easier to see. For an elastic collision along the x-axis, the relative velocity simply changes sign from the initial state to the final state. This is Mazur's equation 5.4. It's one of the most useful equations in the whole book. So it will simplify. Instead of having to use quadratic equations, you can use linear equations when dealing with elastic collisions. v1x final minus v2x final is the negative of v1x initial minus v2x initial. So the minus sign just lets you flip the order of the two terms. So if you want to, you could say v1x final minus v2x final equals v2x initial minus v1x initial. Okay, we can write in one dimension the initial kinetic energy, the kinetic energy before the two objects collide, as 1/2 m1 v1x initial squared plus 1/2 m2 v2x initial squared. That's just 1/2 mv squared object 1 plus object 2 in the initial state before the collision. And then the final kinetic energy, 1/2 m1 v1x final squared plus 1/2 m2 v2x final squared. So that's just 1/2 mv squared, the kinetic energy, first object plus second object in the final state after the collision. And we can add kinetic energies together. Well, we can add energies together. We can add energies together because energy is an extrinsic property. Okay, energy is an extrinsic quantity, so you can say the total kinetic energy of the two objects is the sum of the two objects' kinetic energies. So, because you know the kinetic energy of a system of two objects is the sum of their two kinetic energies. That's a consequence of it being an extrinsic property, which we discussed last time in the context of momentum. Then the initial momentum this is along the x-axis, m1 v1x initial plus m2 v2x initial. The final momentum, m1 v1x final plus m2 v2x final. Now, the big claim is if the final momentum equals the initial momentum, so that's true for an isolated system, and if the relative velocity in the final state is just the negative of the relative velocity in the initial state. So v1x final minus v2x final is just the negative of v1x initial minus v2x initial. So the negative is the same as swapping the two terms. So v1x final minus v2x final equals v2x initial minus v1x initial. If we put these two statements together, I claim that the final kinetic energy equals the initial kinetic energy. So that means kinetic energy is the same after the collision as before the collision, the total kinetic energy. And so then that will tell us that our two definitions, or our two ways of describing an elastic collision, are equivalent. One is that the total kinetic energy is the same before and after, and the other is that the relative speed is the same before and after. And using the relative speed is much more convenient. So if the kinetic, we want to prove that the kinetic energy after equals the kinetic energy before. So let's write kinetic energy after minus kinetic energy before. So if we get that this quantity equals 0, then we know that we've shown that the kinetic energy in the final state equals the kinetic energy in the initial state. So we have this expression minus this expression, and now we can group together the m1 terms and group together the m2 terms. So we have 1 half m1 v1x final squared minus v1x initial squared, and so on. You might remember if you have a difference of two squares, then that's the same as a plus b, a minus b here. So if we take this expression, v1xf minus v2xf equals v2xi minus v1xi, and if we move all the 1's over to the left and move all the 2's over to the right, we have v1xf plus v1xi equals v2xf plus v2xi. And so this expression is the same as this expression, and this expression is the same as this expression. Therefore, we can write that this equals 1/2, and then if we do some rearranging, we can see that this quantity in square brackets is just the difference between initial and final momenta. So for the difference between the final kinetic energy and the initial kinetic energy, we get some factor out front, and then times the difference between the final momentum and the initial momentum. And if the system is isolated, then the difference between the final momentum and the initial momentum will be 0. So then the difference between the final kinetic energy and the initial kinetic energy is 0. So what we've done here is basically just argue that as long as momentum is conserved, then this statement that the kinetic energy is the same in the initial, final, and final states is the same as the statement that the relative speed is the same in the initial and final states. In other words, the velocity just flips sign from the initial to the final states. So this is true for elastic collisions in one dimension. Okay, again, kinetic energy is 1/2 mv squared. It is the energy of motion. Kinetic energy, the total kinetic energy is unchanged in an elastic collision. So for an elastic collision, 1/2 m1 v1 squared plus 1/2 m2 v2 squared for the initial state equals that same sum for the final state. But it's actually much, much, much easier in practice to write equivalently that the relative speed in the initial state is the same as the relative speed in the final state between objects 1 and 2. Okay? And particularly if the objects actually collide with each other, they don't just go past each other, then the relative velocity in the final state is just the opposite of the relative velocity in the initial state. That's equation 5.4 from Mazur. It will be your friend. So the 4 types of collision are distinguished by their value of this restitution coefficient E, little e. 4 types of collision. Elastic collisions. Objects recoil with the same relative speed as before they collided. The total kinetic energy afterward equals the total kinetic energy beforehand. So if you write the relative velocity in the x direction afterward, it's just the minus, the negative of the relative velocity in the x direction beforehand. If you have elastic collisions between 2 objects colliding along the x-axis. In a totally inelastic collision, the objects stick together, so the relative speed afterwards is 0, so the relative velocity afterwards is 0. That's really convenient. It makes the math really easy because there's only one velocity in the final state. The 2 objects stick together, and there's only one v final to worry about. In a collision which is inelastic, the objects recoil from each other but with a reduced relative speed. And actually, you've experienced that when you bounced the super ball off the table, the relative speed of the ball and the floor was a little bit smaller after the bounce than before the bounce. So that it was pretty good, right? So if it were an absolutely perfect super ball, then the relative speed after the bounce would be the same as the relative speed before the bounce. But it's not quite perfect, so the relative speed after the bounce is a little bit less. So it bounces with a little bit lower speed on its way back up than it had on its way down just before the bounce. So that's an example of a restitution coefficient which is close to 1, but it's a little bit smaller than 1. Yeah. And explosive separation actually turns out to be like a totally inelastic collision with the movie played in reverse. We can even see that. So the relative velocity in the initial state is 0. Initially, the 2 objects are stuck together, but later they're moving away from each other. So the final relative velocity is non-zero. By the way, what is the value of the restitution coefficient that describes an explosive separation? I told you that a moment ago. It's infinity, because you're taking something that starts out 0 and you're making it finite, so you have to multiply it by infinity to achieve that. I'll take these 2 rubber bands and I'll kind of squish them and then I'll let go. Oh. If I play in reverse a movie of an elastic collision, what sort of collision would I appear to see? Think about that. Then the relative speed of the 2 objects after the collision the relative speed after is the same as the relative speed before. So it turns out if you play in reverse a movie of an elastic collision, you see an elastic collision. As a matter of fact, one thing that distinguishes an elastic collision is that you can't tell whether the movie is playing forward or backward. So in Mazur's book, there's a profound connection between elastic collisions and reversible processes. So it turns out that if some energy, some of the kinetic energy is transformed, dissipated into incoherent forms, into thermal energy, for example, then that is an irreversible process. So if you play the movie backwards, it doesn't make sense. But for an elastic collision, there is no dissipation of energy. There's no transformation of energy from coherent into incoherent forms. So this, in fact, is reversible. It's a process where if you play the movie backwards, it still looks like good physics. When we collide on a low friction track 2 carts whose masses and initial velocities are known, then the fact that the system is horizontally isolated, that's what the low friction track achieves for us, then that they're not really interacting horizontally with the track. So then conservation of momentum allows us to say that the momentum in the x direction is constant. So then we can say the total momentum of the two objects in the initial state equals the total momentum of the two objects in the final state. That's one equation we can write down, but notice that this one equation has two unknown variables. There's v1x in the final state and there's v2x in the final state. So you have one equation, but two unknowns in the final state. And you know that in order to solve for two unknowns in the final state, you would need two equations. So what is that second equation? Well, knowing something about energy gives us a second equation. And the key is knowing the relative speed of the two objects after the collision, or in particular the relative velocity. So if the collision is elastic, then v1x final minus v2x final is just minus v1x initial minus v2x initial. So this is a nice linear relationship between your two unknowns, because presumably you know the initial velocities. So then you can write down this nice relationship between v1x final and v2x final. So that's one nice relationship between your two unknowns. And here's another nice relationship between your two unknowns using momentum. And then you have two equations and two unknowns. You can figure out the two final velocities. If the collision is totally inelastic, this is my favorite kind, because then v1x final is just the same as v2x final, so there's only one final state variable, only one unknown, and you only need the momentum equation, because you say, well, you see, this variable is just the same as this variable. So that's my favorite case, because the math comes out easily. If the restitution coefficient is given to you, that's a little bit, somebody might concoct a problem where the restitution coefficient is specified. Then you say, okay, v1x final minus v2x final is just minus the restitution coefficient times v1x initial minus v2x initial. Okay, so that might happen once in a while. There's another tricky case. You could say, well, what if a change in internal energy is given? And now, to understand the vocabulary here, it kind of helps to skim through where chapter 5, where Mazur talks about internal energy, and he draws energy diagrams, and he talks about different forms of energy. But in any case, a change in internal energy, it might correspond to a spring releasing its energy, or it might correspond to two objects colliding and crushing the fenders in such a way that the energy of the molecules of the fenders is rearranged. Or it might correspond to things colliding and squishing something. So there are a number of ways that could happen anyway, but it corresponds to energy transformed into some other form. So if you're told what the change in internal energy is, then you can say, well, the kinetic energy of object 1 plus the kinetic energy of object 2 plus the internal energy before the interaction is the kinetic energy of object 1 plus the kinetic energy of object 2 plus the internal energy, all added up after the interaction. And so this would be true for a closed system. So no energy goes in or out of the system, but some energy is transformed inside the system from one form to another. So it might be that two things collide with each other and one of them gets warmer as a result, so that's internal thermal energy. Or it might be the two things collide and one of them gets crushed, and that's a change in internal energy of a different form. Or it might turn out that two things collide and a spring gets squished. Or it might turn out that a spring unsquishes and the things move apart. So in that case, there might be some internal spring energy in the initial state, and then in the final state, that is turned into kinetic energy. So you can transform energy from various forms. So again, it's like bookkeeping. You add up the energy in the initial state, and you add up the energy in the final state. And as long as you've correctly accounted for how it's transformed from one state to the other, and as long as you can draw some kind of box saying that no energy escapes in some unnoticed way, then you can do energy bookkeeping. And when you combine the momentum bookkeeping with the energy bookkeeping, usually you have enough information to determine the final state. What kind of collision is illustrated by this velocity versus time graph? Is it elastic, inelastic, totally inelastic, explosive separation, or what? Well, what is the relative speed in the final state? It seems like in the final state, the two objects have the same velocity. So it seems like the relative speed in the final state is zero. What kind of collision is that? I think that's a totally inelastic collision. So I would say that this is a totally inelastic collision. By the way, can we figure out the ratio of the two masses? See if you can figure it out. I think the upper curve, the red curve, undergoes twice as large a change in velocity as the lower curve, the yellow curve. So I think the object represented in the upper curve has 1/2 the mass of the object in the lower curve. So I think this yellow object has twice the mass of the red object because the red curve goes down by 2 units of velocity and the yellow curve goes up by 1 unit of velocity. So those changes are in the opposite direction, which makes sense for two things that collide. But the magnitudes are a fact ratio of 2 to 1. So I think the yellow object is twice the mass of the red object. What kind of collision is illustrated by this velocity versus time graph? So we have velocity on the vertical axis and time on the horizontal axis. So again, we want to look at the relative speed after versus the relative speed before. So the relative speed after is the size of this difference, and the relative speed before is the size of this difference. So it's the relative speed beforehand is about 3 times as big as the relative speed afterwards. So I would say in this case we have a restitution coefficient of something like 1/3. Okay, so I would say that this is definitely an inelastic collision. So the restitution coefficient is bigger than 0 and smaller than 1. So we call that inelastic. By the way, can we figure out the ratio of the masses? So to figure out the ratio of the masses, we need to compare the two changes in velocity. And it seems like the orange object goes from there down to there. And it seems like the red object goes from there up to there. So I think those two changes are the same size. So I think in this case we have m1 equals m2, or at least they're close. I think they're probably the same, or at least they're very close. I think those two masses are equal because the two objects experienced changes in velocity that were equal in magnitude. Of course, they were in opposite directions, but they were equal in magnitude. So I think this is an inelastic collision between two objects of equal mass. Yeah. Suppose you find an isolated system in which two objects about to collide have equal and opposite momenta. If the collision is totally inelastic, what can you say about the motion after the collision? Well, if the two objects have equal and opposite momenta, then the total momentum in the initial state is 0. And if it's an isolated system, then the total momentum in the final state will be 0, because the total momentum is constant for an isolated system. Now, if the collision is totally inelastic, then the relative speed of the two objects will be 0 after the collision. So not only is the total momentum of the system 0, but the relative speed of the two objects is 0. The only way that can be true is if the system is at rest. Both objects are at rest. You could do that with math if you wanted to. You could say m1 v1 xf plus m2 v2 xf equals 0. And then you can say v1 xf minus v2 xf equals 0. So this first statement is saying that the momentum in the final state is 0. Second statement is saying that the relative speed of the two objects in the final state is 0. So this says v2xf equals v1xf. And therefore you can say m1 v1xf plus m2 v1xf is 0. So that says that v1xf is 0. And then you can also say, so this is m1 plus m2 v1xf is 0. So v1xf must be 0. And then similarly, you can say m1 plus m2 v2xf is 0. So v2xf must be 0. So you could do it with math, or you can say, okay, they're not moving with respect to one another, and also somehow the momentum of the system is 0. So if you have two things that are stuck together, and those two things stuck together have 0 momentum, then they must both be at rest. Imagine making two springy devices, each made up of a dozen or so metal blocks loosely connected by springs, and then colliding the two head on, like two really jiggly objects, maybe like two pieces of Jell-O. It's kind of like two pieces. Imagine taking basically two blocks of Jell-O and colliding them head on. What do you expect the collision to be? Elastic or inelastic or totally inelastic? And well, I guess I made a little video simulating this idea, and it kind of connects to Mazur's idea of energy being transformed from coherent forms into incoherent forms. But I would say that this must be either inelastic or totally inelastic. It's not going to be elastic because you're going to have some coherent energy in which all of the molecules of object 1 and all of the molecules of object 2 are moving together coherently. And then after the collision, the molecules are just going to be jiggling in their own random separate directions. And so then that corresponds to nice coherent kinetic energy being transformed into the thermal energy of molecules just jiggling in their own directions. And the book does a better job of that than I can do, but that's the idea. So often when you have irreversible processes, when you have the dissipation of mechanical energy into thermal energy, when you have the transformation of coherent energy into incoherent forms, those are connected to one another. So inelastic and totally inelastic collisions involve the transformation of coherent energy into incoherent forms, or they involve the dissipation of mechanical energy into thermal energy. And those processes, if played backwards as a movie, would not look like good physics. You would be able to tell, obviously, that something is not making sense, because it appears as if spontaneously thermal energy is transformed into mechanical energy. Here is sort of an eerie reverse video image of a toy called a Newton's cradle, and it consists of a bunch of steel balls hanging by strings, and you can pull one ball back and release it. And if you pull one ball back and release it, you get these beautiful elastic collisions. So coefficient of restitution is approximately 1. So you get these really nice elastic collisions between these steel balls. If I pull back one ball and release it, the only way for the momentum of the final state to equal the momentum of the initial state, and for the kinetic energy of the final state to equal the kinetic energy of the initial state, is if one ball comes out mimicking what the one ball went in doing. And if you pull two balls back, then you get two balls going out on the other side, and so on. So it's kind of fun to see. We'll see. I made a little movie of myself playing with this thing. This argument counts on the collisions being elastic. So if I put a piece of Play-Doh between two of the spheres, it ruins the elasticity of the collisions. And then what comes out is kind of a jumble. So you'll see that momentum is still constant. The momentum afterward is still equal to the momentum before, but you no longer have this nice relationship given by the kinetic energy afterward equaling the kinetic energy before. So you no longer have this nice argument about, like, if there's a relative speed of one unit coming in on the left, then you have a relative speed of one unit going out on the right with one object, or you have two coming in, two going out with that same speed. That argument counts on the kinetic energy of the final state being the same as the kinetic energy of the initial state, in addition to momentum being constant. If you dissipate some of the kinetic energy into thermal energy by putting a piece of Play-Doh between the two spheres, then you see that you no longer get that nice, simple result. And also, if you were to play the result backwards as a movie, it would be obvious that the film is going backwards rather than forwards. So it's an irreversible process. Let's try this. That's pretty good. So again, what if we spoil the elasticity somehow? So we'll take a piece of Play-Doh and we'll put it somewhere in here. Maybe we'll put it here. And now I'll pull one ball back. And what's going to happen? Oh. It's something quite a bit more complicated, I guess, because now it's no longer, so we still have to have, we have one unit of momentum coming in, we have to have one unit of momentum going out, but now the total kinetic energy afterwards is smaller than the total kinetic energy before, and so you can't satisfy those two constraints together by putting all of the momentum into one ball. So we have two balls come out together but at a smaller speed. And I guess we can try it this way also. So the really nice behavior where what comes out on the right looks just like what went in on the left really seems to depend on the fact that these collisions are elastic. It's how you're initial half so then not only do we have to have, let's say all the masses are 1, so then the masses cancel out. So then not only do we have to have the sum of the v's afterwards be the same as the sum of the v's before, but also we have to have the sum of the v squares after be the same as the sum of the v squares before. And again, the only way to make that work is if what comes out looks just like what went in. question. If all three collisions in the figure shown here are totally inelastic, which one or which ones will bring the car on the left to a halt? So in which cases will the car on the left be completely stopped after the collision? So let's look at this middle case first. So you have mass m, velocity v going to the right, and then opposing it you have mass 2m, velocity 1/2 v. So I guess the momentum going to the right is m times v. The momentum going to the left is 2m times 1/2 v, so that's the same m times v. So I guess the total momentum is 0 in the initial state. Total momentum in the final state will be 0. And if it's a totally inelastic collision, then both objects will be brought to a halt. So I think that the car on the left will come to a halt in the middle case. What about the third case? Here we have m times v, and here we have 1/2 m times 2v. I think we can make the same argument that m times v is the same as 1/2 m times 2v. So the initial total momentum is 0. So the final total momentum will be 0. So I guess, and if it's a totally inelastic collision, then I guess this will bring both objects to a halt. What about mv? So you have some momentum to the right in the initial state. So what happens in the final state? Well, this is a brick wall. So there are two ways we could look at this brick wall. One is we could say, well, the brick wall is attached to the earth. So then this is not an isolated system. So then the momentum of the car will be changed by its interaction. Well, if the system is just the car, then the momentum of that car system will be changed by its interaction with the brick wall. If you say the system is the car plus the brick wall, well, actually the momentum of the car plus the brick wall will be changed because the brick wall is interacting with earth. So you say, okay, so I can't really use momentum in this case because somehow there's an impulse given to the brick wall by earth, so the car hits the brick wall and the brick wall is attached rigidly to the earth. So there's some impulse given to the brick wall by earth. It's kind of like I was throwing the medicine ball back and forth with Mary. I had rubber-soled shoes on, she had roller skates on. So when she threw the ball to me, she recoiled. But if I caught the ball or I threw it back to her, I did not recoil because of my interaction with the floor. So we could say, well, the momentum law doesn't really apply here, but intuitively it seems like it's going to hit the brick wall. The brick wall is not going to move, so the car will still be brought to a standstill. That makes sense to me. Or we could say that the system is the car plus the brick wall plus some big massive piece of earth underneath the brick wall. And then you could say, well, that piece of earth underneath the brick wall attached to the brick wall, the whole thing together, so the brick wall plus the earth underneath it, is such a gigantic mass. In fact, maybe we could even say it includes the mass of the earth. So if you wanted to be really fancy about it, you don't have to be this fancy. This is just so the short answer is all three, right? All three of these situations bring the car on the left to a halt. But you want to think about, why does it work in the first case? Well, one way you could say it works is, well, there's some impulse from the earth. Okay. But another way you could say it, I guess, is so here's a more mathematical way to look at the same thing. So we can say, let's let little m be the mass of the car, and let's let big M be some gigantic mass of the brick wall, and maybe even including the mass of some big surrounding chunk of earth. So the initial momentum is just the mass of the car times the Vx initial of the car, because the brick wall is not moving in the initial state. The final momentum is the sum of the two masses times this final velocity of the car plus the brick wall and surrounding earth, because we're told that it's a totally inelastic collision. And you say, okay, well, is the car capable of making this big bunch of brick wall and earth budge? Well, so for a totally inelastic collision, Vx final of the whole thing, right, the car plus the brick wall or whatever is attached to the brick wall, that is this ratio, little m over little m plus big M, just divide out, times this Vx initial of the car. And this ratio goes to 0 in the limit where big M is much, much, much bigger than little m. So actually, one way to look at things like I crashed into the earth is you could say, well, the earth is so much more massive than I am, that effectively, after the collision, I don't budge as long as it's a totally inelastic collision, because this gigantic mass in the denominator is so huge that for all intents and purposes, the final velocity is 0. So that's one kind of more mathematical way to look at it, if you like that. Which of these systems are isolated? While slipping on ice, a car collides totally inelastically with another car. The system is both cars, and we ignore friction. I think that's isolated. So it's on ice, so there's no horizontal interaction with the earth. The two cars are only interacting with each other. So I would say, looking at the x variable, the horizontal coordinate, the system is isolated. That looks good to me. Now, what if, okay, a car collides totally inelastically with another car. The system is one car. Well, that system of one car is not isolated because it's going to interact with the other car. So it's not an isolated system. How about a single car slips on a patch of ice and the system is that car? Well, I think that is an isolated system because it's not interacting with anything outside of the system, at least as far as the horizontal coordinate goes. How about a car brakes to a stop on a road? The system is the car. I would say that's not isolated because the car tires are interacting horizontally with the road. So the car is not an isolated system because its momentum is being changed by its interactions with the road. What about, okay, a ball drops to earth and the system is the ball. Okay, so now we're talking about the vertical coordinate. I think the ball is not isolated because it is under the influence of Earth's gravity. And also you can see that somehow Earth's gravity is causing its momentum to change as it falls toward Earth. A billiard ball collides elastically with another billiard ball on a pool table, and the system is both balls, and we're going to ignore friction. Well, I think that is isolated as long as we're ignoring the friction between the balls and the cloth on the pool table, which maybe for a short time is a reasonable assumption. Over long periods of time, you can't ignore friction on a pool table, but maybe at the very close instant near a collision, you can. So I think this is okay. Billiard ball collides elastically with another billiard ball on a pool table. The system is both balls. Yeah, so I think that the two balls are interacting with one another and not with the table. I guess this is assuming that they're in the middle of the table. They're not right up against the rails of the pool table. And we're assuming that the frictional interaction with the cloth is negligible. So I think 1, 3, and 6. So I guess my answer would be echo, 1, 3, and 6. So here's a page full of results from chapter 5 that we wrote down earlier. So we said momentum conservation lets us say basically mass times velocity added up for the two cars that collide, and that sum is the same in the initial state and the final state. That's if the system is isolated. But then we need a second equation to get our second unknown, and we have this equation if the collision is elastic. We have this equation if the collision is totally inelastic. If the collision is elastic, if the collision is inelastic but not totally inelastic, that's usually hard to figure out, but sometimes the restitution coefficient is given. That's not too often, but so if it is given, then you can work that out. Or sometimes a change in internal energy might be given, and that's often pretty tricky. But if that's true, then we can just do bookkeeping including the energy. So then you say the total energy of the initial state equals the total energy of the final state if no energy enters or leaves the system, and if we know how to account for the change in kinetic energy. So let's try using these results instead of just talking about them in the abstract. 2 carts of mass m1 is 1 kilogram and m2 is 1 kilogram collide head-on on a low-friction track. Before the collision, which is elastic, cart 1 is moving to the right at 1 meter per second, and cart 2 is at rest. What are the 2 carts' final velocities? So we can use momentum, and we can use the fact that the collision is elastic. And in the initial state, we have v1x initial is 1 meter per second. In fact, it's even in plus 1 meter per second. v2x initial is 0. So this is 1 minus 0, and then with a minus sign. So this is minus 1 meter per second. So that gives you v2x final equals v1x final plus 1 meter per second. And in the initial state, this is 0. Also, all of the masses are equal, so we can just cancel out the masses. And this must be 1 meter per second. So I think we have so in the final state, we have object 1 at rest and object 2 moving to the right with the velocity that object 1 had initially. And that is the familiar appearance of 2 objects of equal mass, if one of them at rest, one of them initially moving, colliding elastically. That's like a billiard stop shot, or it's like the collisions we saw on the air track. And you can see that Wolfram Mathematica agrees. I typed this stuff in this obscure Wolfram Mathematica language, and I get v2xf is 1, v1xf is 0. 2 carts of inertias m1 equals 1 kilogram, m2 equals 9 kilograms collide head-on on a low-friction track. Low friction, the system is isolated. Before the collision, which is elastic, cart 1 is moving to the right at 1 meter per second, and cart 2 is at rest. What are the 2 carts' final velocities? Well, momentum lets us write, because it's an isolated system of 2 carts, v1xi m1 v1xi plus m2 v2xi equals m1 v1xf plus m2 v2xf. And we know that this term is 0. And then the fact that it is an elastic collision allows us to write V1xf minus V2xf equals, it's the opposite of the initial state, so that's V2xi minus V1xi. Which is, I guess I should have written it the other way, but this is minus 1 meter per second. So then that tells me that V2xf equals V1xf plus 1 meter per second. Move that over there, move that over there, yeah. Okay, then I get to use the momentum law. So the momentum law gives me, so I'll move this down here, and I get M1 V1xf plus M2 V1xf plus 1 meter per second equals so after the math, V1xf is minus 0.8 meter per second, and V2xf is plus 0.2 meter per second. And that agrees with what Wolfram alpha said. Wolfram Mathematica said V2xf is plus 0.2 and V1xf is minus 0.8. So we have successfully solved our second problem using momentum and energy together. And notice that what this is telling us is that the lightweight object recoiled backwards almost as fast as it came in, and the massive object went forward with just a small fraction of the velocity of the incoming object. So we get a big 0.8 of a meter per second backward velocity for the lightweight object, and we get a small 0.2 of a meter per second forward velocity for the massive object. Here's a variation on that last problem. So instead of a 1:9 ratio of masses, how about a 1:14 ratio of masses? And I think you're going to do some similar problem where it says a baseball and a basketball collide. I mean, a baseball is tossed into a stationary basketball, and if the ratio of masses is about 15:1, or let's say 14:1, then you don't have to do it numerically, but just draw some arrows. You say, okay, when a lightweight object recoils elastically from a much more massive object, the lightweight object basically reverses direction. Okay, so I mean, like, you know, your super ball collides with the earth, it just reverses direction. Same kind of, almost the same speed in the other direction. So you can say a similar thing for the baseball hitting the much more massive basketball. It essentially just reverses direction. It's not exactly, this is plus 1 meter per second Mathematica. Wolfram Mathematica says This is actually 13/15 of a meter per second in the other direction. So it's not quite 100%, but it's like, I don't know, 87% of its initial speed in the opposite direction. Now, this basketball, or the 14 kilogram object, is almost, well, it's initially at rest. And so you say, what happens after the collision? Well, you see, if all of this initial momentum went to the M2 here, the 14 kilogram object, then you would just take this line and divide it by 14, and you would get this line. But in fact, you have this momentum is reversed to this momentum. So if we take this thing and we turn it into momentum, we would basically draw something like 14 times as long. And then meanwhile, you have, here's the initial momentum of the lightweight object. Let's say it's just times 1, so it's the same. And then here's the final momentum, so somehow we have to account for that too. So you see, we reverse its direction. So if we reverse its direction, because you know that, so you know that P2 x initial is 0. So then you know that P1x initial plus P2x initial is P1x final plus P2x final, but this is 0. So you know that P2x final must be P1x initial minus P1x final. Yeah. So you see, this would be like P2x final. Oh, sorry, this is like P1x initial. P1x initial, and this is like minus P1x final. Yeah, so you take P1x initial minus P1x final, you combine those, that should be like P2x final, but then we have to scale down by the masses to go from momentum to velocity. So if you're going to draw velocity arrows, I think you take this and kind of shrink it by about a factor of 15. And you see, you notice, what does the number work out to? You see this number is 2/15. So that kind of makes sense. You have 1 unit for the incoming, another unit for reversing the outgoing, and then you have the 15 downstairs because you're kind of scaling by this mass. So I said 14, 15. So, okay, I guess if you do it exactly, you get 15. We said, well, divide by 14 to go from incoming momentum to outgoing momentum. So I'm kind of waving my hands. So you could just do it exactly, but I think it's kind of interesting to try to do it intuitively. You say, lightweight object bounces off of a much more massive object elastically. Well, it basically just reverses its velocity vector. Then you say, okay, now how do we conserve momentum? Well, you take this momentum, and you also take the reverse of this outgoing momentum, and somehow those two things, if you add them, are the momentum that you have to give to this more massive object. But to turn that into a velocity arrow, you shrink it down by this ratio of masses. So you shrink it down. So that's 2 units, and you would divide by 14 if you just do it hand waving. In real life, you solve it with exact numbers, you get 2/15. So I think that's kind of fun. I think it's kind of fun to reason through that. Okay, 2 carts. First one, mass M1 is 1 kilogram. Second one, mass M2 is 9 kilograms. They collide head-on on a low-friction track. So it's a nice isolated system colliding on the x-axis. Before the collision, which is totally inelastic, cart 1's moving to the right at 1 meter per second. Cart 2 is at rest. What are the 2 carts' final velocities? My favorite kind of collision is totally inelastic because the math comes out so much more simply. So totally inelastic means that V2xf equals V1xf. Okay, so then momentum tells us that M1 V1x initial plus m2 v2x initial equals m1 v1x final plus m2 v2x final. But let's just call this vx final because it's the same. v1x final is v2x final. We'll just call it vx final. And you know this is 0 because v2x initial is 0. So then you get m1 v1x initial equals m1 plus m2 vx final. You see they have the same vx final, so this really makes the math nice. So you have vx final is m1 divided by m1 plus m2 v1x initial. And what is that? It seems like it is 1/10 of 1 meter per second. So that is plus 0.1 meter per second. Let's see what Wolfram Mathematica said. Oh, look at this. Wolfram Mathematica said they both equal plus 0.1. I love totally inelastic collisions. Two carts, mass m1 is 1 kilogram, mass m2 is 1 kilogram, collide head-on on a low-friction track. Before the collision, cart 1 is moving to the right at 2 meters per second. Cart 2 is moving to the left at 2 meters per second. After the collision, cart 1 is moving to the left at 1 meter per second, and cart 2 is moving to the right at 1 meter per second. Let the system be cart 1 plus cart 2. With the given values, is the system's total momentum the same before and after the collision? Well, I think it is because the total momentum before the collision is 0, and the total momentum after the collision is 0. So I think this is consistent with it being an isolated system. What is the coefficient of restitution, E, for this collision? Well, I guess I put the answer down here. Normally there would be like a pause between slides. So the restitution coefficient, so remember that v1xf minus v2xf is minus E times v1xi minus v2xi. So it's basically the ratio of the relative speeds before and after. So v1xf minus v2xf is minus 1 meter per second minus plus 1 meter per second. And that's minus E times v1x initial is plus 2 meters per second, and then that's minus 2 meters per second. So this tells you minus 2 meters per second is minus E times plus 4 meters per second. So I would say E is 1/2. Yeah. So I would say our restitution coefficient is 1/2. And you can see the relative speed, that's the magnitude of the relative velocity. The relative speed after the collision is half of the relative speed before the collision. Before the collision, the relative speed is 4 meters per second. After the collision, the relative speed is 2 meters per second. So restitution coefficient is 1/2. Now we have an example where initially we have two carts, they're both 1 kilogram, two carts that are squished up against each other. They're connected to each other by a compressed spring, and that compressed spring is somehow storing energy. It's internal energy in the spring. And we are told that the stored energy in the spring is 4 joules. And that initial stored energy in the spring will be released, and it will turn into kinetic energy of the carts. So initially, both carts are at rest, so there's no kinetic energy. So let's do energy bookkeeping. So energy. So in the initial state, we have K1I plus K2I plus EI spring. And then in the final state, okay, and this is going to be 0. And this is going to be 0. And then in the final state, we have K1F plus K2F, and then there's no energy left in the spring. So E final spring will be 0. So this will be 0 in the final state. Okay, so then we can say this is 0 plus 4 joules. So 4 joules equals 1/2 M1 V1 F, I guess I could say X, but V1X F squared, because it's only moving in one dimension, plus 1/2 M2 V2XF squared. That's what energy tells us. So the initial stored energy in the spring equals the final sum of the kinetic energies, because there's no stored energy in the final state, just kinetic. The initial state has no kinetic energy, just stored energy in the spring. And then we have momentum. So momentum tells us, so the initial momentum is 0. So let's just say 0. 0 is M1 V1XF plus M2 V2XF. And then you know that M1 equals M2, so this will actually tell us that we have M1 equals M2, so that gives us a V2XF equals V1XF. And then, so we can eliminate one of those. We can move this down here, and we say 4 joules equals 1/2. Well, let's just say M, right? So let's say M equals M1 equals M2. M, and then we can just call this V final, or Vx final. Okay, M Vx final squared, and then there's another copy of the same thing, so we can just erase the 1/2. You see, we have 1/2 M Vx final squared plus 1/2 M Vx final squared. Yeah, here's one of them, here's the other one, and they're equal because the masses are equal, and momentum tells us that the two velocities are equal, or the two speeds are equal. Sorry. Oh, whoops, this is a minus, yeah, so this is a minus sign, sorry. But, yeah, okay, there's a minus sign. So they're the same magnitude, but they're in opposite directions, sorry. But we'll just call that, well, all right, we'll call it VXF anyway. I mean, we're going to square it, so I think it's okay. Okay, so then, you know what, I'm going to call this V2XF so I don't confuse anybody. So I'll call this V2XF. That's fine. V2XF. And then we'll just reverse it to get V1XF. So then that gives us V2XF equals, I guess we have to use our brains a little bit to figure out which direction they're moving, because you see, there's nothing in the problem that tells you which one's moving to the right, which one's moving to the left, unless you look at it and you say, when they separate, number 2 is going to go to the right, number 1 is going to go to the left. The math won't tell you that on its own. So V2XF must be the square root of 4 joules divided by this mass, which is the square root of 4 joules divided by 1 kilogram, which is going to be 2 meters per second. Okay, so I guess that gives us V2x final is plus 2 meters per second, and V1x final is minus 2 meters per second. Yeah, to get the signs, you have to look at this picture and see which one's going to go to the left, which one's going to go to the right. And what does Wolf from Mathematica say? Wolf from Mathematica says V2XF is plus 2 and V1XF is minus 2. How did it know that? Oh, I told it V2XF is bigger than 0 because that's what the picture says. Okay, wasn't that fun? So we got to use energy in the form of joules. So we said, okay, we had 4 joules of spring energy that somehow found its way into the final state's kinetic energy. Here's another problem that's almost the same as the previous problem. A system consists of a 2 kilogram cart, and I drew it a little bigger, so you know that one's bigger, and a 1 kilogram cart attached to each other by a compressed spring. Initially, the system is at rest on a low friction track. So they're at rest, the whole system's at rest. It seems like they're not moving with respect to each other, so both initial velocities are 0. When the spring is released, an explosive separation occurs at the expense of internal energy of the compressed spring. If the decrease in the spring's internal energy during the separation is 10 joules, what is the speed of each cart right after the separation? So just to be concrete, let's say that the initial energy of the spring is 10 joules and the final energy of the spring is 0. Now, it could be that you start out with 20 and you end up with 10. It won't make any difference because what matters is the balance between the left and right sides of this equation. So let's say we start out with 10 joules in the spring and we end up with nothing in the spring. So that's the same equation we wrote down last time because there's no initial state kinetic energy. There is spring energy. The final state, we have these kinetic energies, and let's say we've diminished all of the spring energy. You see, you could have instead just said this is E spring initial minus E spring final. You could have just moved that over to here, and that would be your change, your decrease in spring energy. Oh, so it's not 4 joules anymore, it's 10 joules. 10 joules is the sun, okay, yeah. So here's 10 joules on the initial state energy, and then here's 1/2 m1 v1 xf squared plus 1/2 m2 v2 xf squared, and this is 0 remaining spring energy. By the way, writing down this equation is, to write down this equation, we have to think a little bit. We have to say, well, the system consisting of the 2 carts and the spring is a closed system. So the total energy in that closed system is constant. That's a little bit of a step of reasoning you have to make. So you say, okay, well, if we draw a box around this system that consists of the 2 carts and the spring, then energy can be shuffled around between the constituents. You see how energy goes from here into here, but it doesn't leave that system as a whole. So that's an important mental step you have to make. So then, so energy, let's just say that the 10 joules initially stored in the spring equals the sum of the 2 final state kinetic energies. We can say that because the system is closed and because the initial kinetic energy is 0. Momentum, the initial state momentum is 0, so it's 0 on the left side. So m1 v1 x final plus m2 v2 x final. So that tells us that v2 x final is minus 2 v1 x final. Yeah. Right, because this should be minus m1 over m2. m1 over m2 is 2, yeah. So then we get 10 joules is 1/2, and then this is 2 kilograms, and this is v1 xf squared, and then this is 1/2, and this is 1 kilogram, and then this is, okay, so v2 xf is minus 2, yeah. Then we have minus 2 v1 xf, and then we can square it. So we square it, the minus sign goes away. So this says 10 joules equals 4 on those 2 divided by 2 is 1 kilogram times v1 xf squared plus, and then this is 4, right? Minus 2 squared is 4. So it's 4 times 4 is 2 kilograms times v1 xf squared. Yeah, so there's 2 times 1/2 is 1. Here's 4 times 1/2 is 2. So then we have 3. So the sum is 3 kilograms times v1 xf squared. So then we get v1 xf. Oh, you can't read that. Oh no. Okay, so V1XF is going to be, the sign for this problem has to come from the picture. So minus, we have 10 joules over 3 kilograms square root, which is minus 1.83 meters per second. And then V2XF must be just twice that with the opposite sign. So that's plus 3.65 meters per second. And okay, and Wolfram Mathematica agrees with me. So V2X final is 3.65 and V1X final is minus 1.83. Good. A battery-powered car with bald tires sits on a sheet of ice. Bald tires, sheet of ice. That's telling you no friction. So no horizontal interaction with the ice. Friction between the bald tires and the ice is negligible. The driver steps on the accelerator, but the wheels just spin frictionlessly on the ice without moving the car. Is the car an isolated system? And again, we're considering only the coordinate along the car's axis. In other words, does nothing outside the system push or pull on anything inside the system? Well, if the system is the car, I would say that system is isolated because, yeah, there are no external influences pushing or pulling, and therefore we expect the momentum of the car to be constant. Is it a closed system? In other words, is negligible energy transferred in or out of the system? Well, there is the battery is causing the wheels to spin faster and faster, but I guess that battery is inside the car. So the energy source is inside the car. And you say, well, if they're spinning frictionlessly, I guess they're not heating up the ice, so maybe there's no thermal energy leaving the car. So in this idealization, I think this system is both isolated and closed. Or I would say, how about isolated, yes, closed, very nearly so, yes. Because in real life, maybe there's a little bit of acoustical energy leaving from the sound of the tires, and maybe friction is very, very small, but still maybe there's a little bit of thermal energy escaping somehow. In real life, it's very difficult to get a 100% closed system. But you could say, yeah, for all intents and purposes, this is a closed system because there's no mechanism for any significant amount of energy to escape or come in. So I would say D, I like D delta. It's certainly isolated and it's very nearly closed. Yeah. A battery-powered Aston Martin car with James Bond-like spiked tires sits on a sheet of ice. Agent 007 steps on the pedal and the car accelerates forward. Is the car an isolated system? Again, we're considering the horizontal coordinate. I would say no, it's not an isolated system because the spikes cause a horizontal interaction, a push between the ice and the car. So the ice is going to push the car forward. So there's some kind of interaction horizontally between the car and the ice, which is going to cause the car to accelerate. And you know that because you look at it, you say, well, the car's momentum is changing. And it's changing because of its interaction with the ice. So I would say it's not isolated. Is it closed? Well, is there any significant energy transferred in or out of the system? It actually might be closed, or mostly closed. Yeah, isolated, no. Closed, very nearly so, yes. I think that's true. So isolated because it's not isolated because there's an obvious mechanism for momentum to get into the system, as you can tell from the fact that it's accelerating. And also, the spiked tires are pushing against the ice, which is outside the system. But we haven't identified any mechanism for energy to get in or out of the system consisting of the car. Now, you see, there is energy flowing out of the battery. The battery has stored chemical energy, and that energy is being converted into the kinetic energy of the car. So you have the internal energy of the battery is decreasing, and the kinetic energy of the car is increasing. But all of that is happening within the boundary of this system which consists of the car. So I like B here, bravo. Isolated, no. Closed, very nearly so, yes. So you have to kind of use your like lawyer-like brain for this. A battery-powered Aston Martin car with James Bond-like spike tires sits on a sheet of ice. Agent 007 steps on the accelerator and the car accelerates forward. All the while, a high-tech solar panel on the car's roof rapidly charges the car's battery. Is the car an isolated system, considering only the horizontal coordinate along the car's axis? No, I would say it's not isolated because the spikes allow for a pushing interaction between the ice and the tires. And so the result is that the car will accelerate so that its momentum will change. So the ice is pushing on the car. Is it a closed system? Is negligible energy transferred in or out of the system? Well, it's not a closed system. The sun is charging the battery. So you see in the previous slide, the battery's internal energy was being depleted, and that's the source of the kinetic energy of the car. Now, the sun's energy is coming in and charging the battery, so there's energy flowing into the system from the outside. There's solar energy flowing into the system from the outside to charge the battery, and then the battery is making the car go. So somehow, ultimately, the source of the car's kinetic energy seems to be the sun. So that's outside of the system. So this is neither closed nor isolated. I like D, delta here. Isn't this fun? A battery-powered Aston Martin with James Bond-like spike tires sits atop an iceberg that floats in the North Sea. Agent 007 steps on the accelerator and the car accelerates forward. What happens to the iceberg? Well, if the car accelerates forward, the iceberg accelerates backward. Yeah, I like that. So the momentum of the car plus iceberg system is probably constant, assuming that the friction, there's like, there's like some, like you have air drag or something falling through the air, there's water drag for the iceberg moving through the ocean. So there might be some frictional interaction between the iceberg and the water, but let's neglect that. Let's say that's pretty small. So the car accelerates forward, so the iceberg must accelerate backward, although the iceberg is much more massive than the car, so the ratio of changes in velocity will be, so the car will experience a big forward change in velocity, and the iceberg will experience a very small backward change in velocity. All the while, a high-tech solar panel on the car's roof rapidly charges the car's battery. Ignore any friction or viscosity, drag, etc. between the water and the iceberg. Which statement is true? The car alone system is isolated but not closed. I think that's not true because the car is not isolated and the car is also not closed. The car is being charged by the sun, so that's energy flowing in. And the car is pushing against the iceberg horizontally, and the car is accelerating, so its momentum is changing, so it's not isolated. The car plus iceberg system is isolated but not closed. I think this is true. You see, so the momentum of the car plus iceberg system should be constant if you ignore the water drag. If you say, okay, there's negligible friction between the water and the iceberg. So in that case, the car accelerates forward, the iceberg accelerates backward, but that car plus iceberg system has a constant momentum. But there's energy coming in from the sun, so I think it's isolated but not closed. I like that. The car plus iceberg system is isolated but not closed. I like that. The iceberg alone system is isolated but not closed. Well, no, the iceberg is not isolated because the car is pushing against it. And we don't know whether the iceberg system is closed. The iceberg system, is it closed? It's also no, the iceberg system is neither isolated nor closed because actually the car is changing the kinetic energy of the iceberg and the car is also changing the momentum of the iceberg, both by a tiny amount, but still, so I don't like that. The car alone system is isolated and closed. Well, the car alone system is not isolated and it's not closed. Car plus iceberg system is isolated and closed. The car plus iceberg system, I would say, is isolated, yes, but closed, no. So I don't like that. The iceberg alone system is isolated and closed. Well, I would say the iceberg alone system is not isolated. And yeah, it's not closed because its kinetic energy is being changed by the car. And we found one that's true. So there we go. I like B. Bravo. Ha! Wasn't that fun? Okay, so an isolated system has no mechanism for momentum to get in or out of the system from or to outside of the system. This means nothing outside of the system can push or pull on anything inside of the system. Soon, when we get to chapter 8, very, very soon, we're going to say no external forces act on the system. This will make more sense when we discuss forces, which I think will happen in another day or two. A hugely important idea in physics is that if the parts of a system interact only with each other, in other words, if they do not push or pull on anything outside of the system, then the total momentum of that system does not change. Hugely important. We call that, well, we basically call that the momentum law. Yeah. A closed system has no mechanism for energy to get in or out of the system. The examples we've come up with so far are contrived, but soon we'll learn to calculate the energy stored in springs, and we'll learn to calculate the energy stored in Earth's gravitational field, and so on. And then the concept of a closed system is much more useful once we learn how to account for the many ways that energy can be stored. Also, if you can quantify the energy that's stored, then you can also, maybe you can estimate the energy that may go in or out and say, well, that's negligible. Maybe it's like 1%, so we won't worry about it. So once we can quantify these conversions of energy in, for example, gravitational potential energy in Earth's gravitational field, or spring potential energy stored in a spring, the idea of whether a system is closed, or at least for all intents and purposes it's closed, will make more sense. Accounting for movement of energy in or out of a system will make much more sense when we discuss work. And we're going to discuss work just after forces. By the way, impulse is a transfer of momentum across the system boundary. Work is a transfer of energy across the system boundary. But we won't see that till chapter 9. I put 2 carts on a low friction track with a compressed spring between them. I release the spring by remote control, which sets the carts moving apart. What system is isolated? Okay, low friction track, compressed spring between them, release the spring by remote control, carts start moving apart. Is one cart isolated? No, because it's being pushed on by the other cart. Is the cart plus the spring plus the other cart isolated? I think yes, because it's only the parts of that system that are interacting with each other. They're not pushing or pulling on anything outside. We're considering the horizontal axis. One cart plus a spring. No, one cart plus a spring is not an isolated system because the other cart is pushing on that system. So I only like B here. Bravo. Cart plus spring plus the other cart. That is an isolated system. I put 2 carts on a low friction track with a compressed spring between them. I release the spring by remote control, which sets the carts moving apart. Is the cart plus spring plus the other system closed? Cart plus spring plus other cart. I think so, because we can account for the energy. So energy goes from the compressed spring to the kinetic energy of the carts, but there's no friction, so there isn't any energy being dissipated into thermal energy by friction. So as long as we can neglect things like the sound, the acoustic energy escaping, and as long as friction is truly negligible, I would say that is a closed system. In fact, that is why we were able, in similar problems, to say, aha, the change in the spring's energy somehow must account for the change in the kinetic energy. Remember, initially we had no kinetic energy, but we had some energy stored in the spring, and then in the final state we had the kinetic energy. We had the kinetic energy of the 2 carts, but there was no stored energy left in the spring, and we could do that energy bookkeeping. So a closed system, or at least closed for all intents and purposes, a closed system allows for this energy bookkeeping, which is very useful. So I'd say yes, for all practical purposes, because the system's total energy, kinetic 1 plus kinetic 2 plus the energy of the spring, that sum is the same before and after releasing the spring, and other tiny transfers of energy like escaping sound and so on are negligible by comparison. So yes, I like A. Yes. Cool. I put 2 carts on a low friction track with a compressed spring between them. I release the spring by remote control, which sets the carts moving apart. This is starting to sound familiar. Is the spring alone a closed system? No, because the spring is giving up energy and is transferring that energy to the kinetic energy of the carts. So the spring alone is certainly not a closed system because energy is flowing out of the spring. It's being transferred out of that spring to the kinetic energy of the carts. So no, because it transferred energy to the carts, which are outside of what you're now calling the system. Yeah, B. See, so where you draw your system boundary makes a big difference in the usefulness of the conservation laws. I put 2 carts on a low friction track with a lighted firecracker between them. The firecracker explodes, which sets the carts moving apart. Is the car plus firecracker plus other cart system closed? Yes, by analogy with the cart plus spring plus cart system. Maybe. Yes, for some other reason. No, because realistically, some of the firecracker's energy will escape in the form of heat, flying debris, etc. So really, energy conservation only provides some upper limit on how much energy you can put into the carts, because some unknown amount of energy from the firecracker will just disappear into the environment. Counting for where the energy goes is more difficult here than for a simple spring. I like C here, Charlie. I hope you understand or are starting to understand what closed means now. But you see, so a system is closed if we can account, well, if we can draw a boundary around the system, and that says no non-negligible energy goes in or out of that system when we draw the appropriate boundary around it. So we are now done. That's the end of the Chapter 5 lecture. So we'll see you in class for worksheet number 5.